WIMP detection. Physicists have been searching for these particles since the 1980s, and the fact that we still haven't found one is starting to feel less like bad luck and more like a fundamental problem. WIMPs, or weakly interacting massive particles, were supposed to be the obvious answer. The theory goes like this. They're particles that only interact through gravity and the weak nuclear force, which makes them nearly impossible to detect, but also explains why they don't emit light. They'd have a mass somewhere between 10 and 1,000 times that of a proton, and if they exist, billions pass through your body every second. We've built detectors the size of swimming pools, buried them a mile underground to block cosmic rays, cooled them to near absolute zero, and waited for a single WIMP to hit a xenon atom hard enough to produce a tiny flash of light. We've been doing this for 30 years. The detectors have gotten 1,000 times more sensitive. Still nothing. Either WIMPs are far more weakly interacting than we thought, or they don't exist at all, and we've been chasing the wrong thing for 3 decades. Some physicists have quietly moved on. Others have doubled down, arguing we just need bigger detectors and more time. The debate is ongoing, the funding is still flowing, and nobody's sure what happens if we spend another 30 years and find nothing. We've invested billions into experiments designed around a particle that might not exist. Modified dynamics. This theory says we've been looking for dark matter particles when the real problem is that we don't understand gravity at large scales, and it refuses to die because it keeps being right about things it has no business predicting. Modified Newtonian dynamics, or MOND, was proposed in 1983 as a way to explain why galaxies rotate faster than they should based on visible matter. Instead of adding invisible matter, MOND says gravity behaves differently when accelerations get extremely small, like at galaxy edges. And it works disturbingly well. You can plug in the visible mass of a galaxy, and it'll predict the rotation speed with shocking accuracy. Not just for one galaxy, for thousands of them. It predicts things dark matter models struggle with, like the precise relationship between a galaxy's visible mass and its rotation curve. The problem is that MOND falls apart at larger scales. It doesn't explain gravitational lensing as well. It struggles with galaxy clusters, and it can't account for the cosmic microwave background without adding components that start to look like dark matter anyway. So it's stuck in limbo. Too successful at galaxy scales to dismiss, but not successful enough at cosmic scales to replace dark matter. The fight has been going on for 40 years. The theory that says dark matter doesn't exist has spent 4 decades predicting things dark matter models can't, which is deeply annoying to everyone involved. Axion Cosmology. There's a particle that might fill the entire universe, weigh almost nothing, and somehow account for most of the mass holding galaxies together. And the weird part is that axions weren't invented to explain dark matter at all. In the 1970s, physicists noticed the strong nuclear force should violate CP symmetry, which would cause neutrons to have an electric dipole moment. But they don't. The solution required a new particle, the axion. It would be incredibly light, billions of times smaller than an electron, and interact so weakly that trillions pass through you every second. Then someone did the math and realized the early universe would have produced them in staggering quantities, enough to account for all the dark matter. To give you a sense of scale, if axions make up dark matter, there would be about 10 million in every cubic centimeter of space around you. That's 10 million in a sugar cube. They'd form a quantum field permeating the galaxy, oscillating at a frequency determined by their mass. Detecting them requires different technology than WIMP searches. Axion detectors use strong magnetic fields to convert axions into photons we can measure. Several experiments are running now, scanning different mass ranges. If axions are real, we might find them in the next decade. We invented this particle to fix an unrelated equation, and accidentally may have solved the biggest mystery in cosmology. Primordial Remnants. What if dark matter is just black holes left over from the first second of cosmic history, and every time someone rules it out for one mass range, someone else finds a new range where it works? Primordial black holes aren't like stellar black holes. They formed in the first fraction of a second after the Big Bang, when quantum fluctuations could collapse before expansion pulled things apart. These could range from a fraction of a gram to hundreds of solar masses, and they'd be gravitationally identical to any dark matter. The appeal is obvious. Black holes exist, so this doesn't require new particles, just accepting that many small black holes formed early. Microlensing surveys put tight constraints on certain mass ranges, but then LIGO detected black hole mergers that didn't fit stellar models, and people wondered if some could be primordial. The debate reignited. Right now, viable parameter space sits in narrow windows: very light, around asteroid mass, or intermediate mass, a few to a few hundred solar masses. To account for the Milky Way's dark matter, you'd need trillions of asteroid mass black holes or millions of intermediate mass ones. Recent studies tightened the windows but haven't closed them. The solution might just be tiny ancient black holes everywhere. Sterile sectors. In 2014, multiple teams reported detecting a faint X-ray line at 3.5 kilo-electron-volts from galaxy clusters, and for a moment, it looked like we'd found dark matter decay. Then the signal got messy. Follow-ups were inconclusive, and nobody's sure what happened. Sterile neutrinos are hypothetical particles that don't interact via standard model forces except gravity. Regular neutrinos interact through the weak force, letting us detect them. Sterile neutrinos wouldn't. They'd be invisible except for gravitational pull, and their potential to rarely decay into a photon and regular neutrino. That decay produced the X-ray signal people thought they saw. If they exist, they'd be much heavier than regular neutrinos, with kilo-electron-volt masses, and the early universe produced them in enormous numbers. They'd clump like cold dark matter, but their decay gives us a way to see them. A sterile neutrino might decay once every few billion years. Detecting that requires instruments sensitive enough to pick up a handful of photons against a noisy background. The signal matched predictions too well, making people suspicious. Other telescopes saw it, didn't see it, or saw something at the wrong intensity. Recent analyses suggest it might be instrumental artifact. But sterile neutrinos are still theoretically motivated. They could explain matter-antimatter asymmetry and show up in standard model extensions. It barely interacts, we're not sure it exists, and if it does, it might explain 3 cosmic mysteries. Self-interacting halos. The standard cold dark matter model assumes dark matter particles almost never interact with each other. But what if that's wrong, and dark matter is doing things to itself we can't see? Self-interacting dark matter proposes particles collide and scatter far more often than thought, changing how galaxies form. The theory emerged because cold dark matter predicts galaxy centers should be denser than observed, the core cusp problem. Simulations produce sharp density peaks, but observations show flat cores. Self-interacting dark matter solves this by letting particles redistribute through collisions. Over billions of years, this smooths density. Distribution. It's like gas reaching equilibrium, except invisible and we only know from galaxy shapes. Even with strong interactions, a particle might collide once every few billion years. That sounds rare, but with trillions of particles and billions of years, collisions reshape structure. The interaction needs fine-tuning. Too strong and galaxies don't form. Too weak and the problem remains. Observations suggest 1 collision per particle per billion years works. The implication is that dark matter might have rich physics, its own force carriers, maybe analogous to electromagnetism, dark photons, dark atoms, even dark chemistry, invisible and only detectable gravitationally. There's entire invisible physics happening that we only know from galaxy shapes. By the way, if you're enjoying learning about these theories, I post content like this regularly. I'd appreciate if you subscribed. Thanks. Thermal relics. What if dark matter isn't cold, meaning slow-moving, but warm, meaning faster? And temperature determines whether small galaxies form or get erased. Warm dark matter sits between cold and hot in particle velocity. Cold particles clump at all scales. Hot particles smooth structure at small scales. Warm is middle ground. fast enough to suppress smallest galaxies, slow enough to allow large structure. This matters because cold dark matter predicts more satellite galaxies than observed. Simulations say hundreds or thousands of dwarfs should orbit the Milky Way. We've found dozens. Either we're missing them or they never formed. Warm dark matter explains the latter by cutting off structure below a mass scale. Particles would have kilo-electron-volt masses, and higher velocities prevent collapse into smallest halos. This creates a cutoff. Nothing smaller exists. Lyman alpha forest observations constrain how warm dark matter can be. Current data allows masses above 3 kilo-electron-volts, suppressing structure below 1 billion solar masses. That eliminates the missing satellites problem. The challenge is weak theoretical motivation. It's not solving unrelated physics problems, just adjusting temperature to fit observations. Some see fine-tuning, others see following data. Temperature will never measure matters for whether small galaxies exist. Ultralight bosons. This theory says dark matter particles are so light they don't behave like particles over galactic distances. They behave like quantum waves, and interference patterns solve problems cold dark matter can't. Ultralight bosonic dark matter proposes masses around 10 to the negative 22nd electron volts. That's 28 orders of magnitude lighter than an electron. At that mass, the de Broglie wavelength stretches to thousands of light years. Inside galaxies, you wouldn't have particles, but a coherent quantum field oscillating and interfering. The wavelength sets a minimum structure scale. Anything smaller gets washed out by quantum uncertainty. This solves the core cusp problem because quantum pressure prevents tight clumping. It addresses missing satellites. Smallest galaxies can't form because wavelength is too large. The particle's wavelength would equal the distance from the Sun to the nearest star. Quantum mechanics and cosmology overlap. Interference effects play out over kiloparsecs. Simulations produce cores instead of cusps, showing wave-like patterns detectable through lensing. The challenge is fine-tuning. Too light and galaxies don't form. Too heavy and you're back to cold dark matter. Observations constrain mass to a narrow window around 10 to the negative 22nd electron volts. Acts like particle and wave across entire galaxies. Hidden photons. If dark matter has its own electromagnetic-like force mediated by dark photons, we'd only see effects when sectors interact at boundaries, and experiments are looking now. Just like photons carry electromagnetic force, dark photons would carry dark electromagnetic force between dark matter particles. They'd be forcing carriers in a hidden sector. The key is kinetic mixing, where dark photons occasionally convert to regular photons. The probability is incredibly small, controlled by the mixing angle, but not zero. In rare cases, dark photons could decay into electron-positron pairs, or convert to detectable photons. The mixing angle needs to be smaller than 1 part in a billion to have avoided detection. That's a rate so low you'd need trillions of interactions before seeing one signal. Experiments look for anomalous photon signals in accelerators and unexpected electron-positron pairs from space. If dark photons exist with mega-electron-volt to giga-electron-volt masses, they'd affect dark matter clumping and early universe interactions. They might explain standard model anomalies. Theoretical motivation is strong because hidden sectors show up in many standard model extensions. But searches are hard. You're looking for tiny excesses in specific energy ranges with brutal backgrounds. Building detectors for invisible light that might not exist. Mirror symmetry. What if every standard model particle has a mirror partner interacting only gravitationally and 2 complete physics sets exist side by side without touching? This theory proposes exact copies of all particles existing in a parallel sector. Mirror particles would have same masses and follow same forces, but sectors are decoupled. Only gravity connects them. This makes mirror matter a perfect dark matter candidate. Invisible, clumps gravitationally, doesn't emit light because mirror photons don't interact with normal atoms. The theory has roots in explaining matter-antimatter asymmetry. The early universe produced equal normal and mirror particles, but they evolved separately. We see the normal sector and interpret mirror as dark matter. Some versions allow weak interactions between normal and mirror photons, producing detectable signals. There's the neutron lifetime anomaly. Neutrons decay faster in beams than bottles. One explanation is some oscillate into mirror neutrons and disappear. If real, there could be duplicate periodic tables forming mirror stars, planets, galaxies, occupying our space but invisible. We'd walk through mirror air, buildings could overlap, and we'd never know because gravity is the only connection. The problem is weak observational evidence. It explains dark matter, but so do many theories, and makes no unique predictions. It's testable through neutron oscillations and photon detectors. So far, nothing. Everything doubled, non-visible. Superfluid condensates. This theory says dark matter isn't particles but a superfluid with zero viscosity, and phonons rippling through it are what we mistake for particle interactions. Superfluidity normally shows up at low temperatures in liquid helium. Below critical temperature, fluid loses friction and flows forever. It climbs container walls, forms quantized vortices, conducts heat perfectly. Superfluid dark matter says it exists in this phase throughout galaxies, with kiloparsec coherence. Dark matter particles condense into collective quantum states, and excitations, phonons, mediate interactions mimicking both dark matter and modified gravity. Here's the interesting part. It reproduces Mond's success at galaxy scales while behaving like cold dark matter at larger scales. Phonons create effective force looking like modified gravity in low acceleration regimes, explaining rotation curves. But at high accelerations, the superfluid behaves like pressureless fluid, matching standard predictions. It's a hybrid, taking the best of both. The healing length would be around a kiloparsec. Dark matter in galaxies isn't independent particles, but a single macroscopic quantum object, with disturbances propagating as sound waves at hundreds of kilometers per second. The theory makes testable predictions. Phonons should create distinctive lensing signatures, affect dark matter distribution in collisions like bullet cluster, might produce detectable gravitational waves when galaxies merge. Some predictions match observations better than cold dark matter. The challenge is requiring specific conditions for the phase, including precise relationships between particle mass, interaction strength, and temperature. Fine-tuning required. Entropic gravity. What if we've spent a century looking for particles when gravity itself isn't fundamental, but emergent from quantum entanglement, and dark matter is a side effect of how space-time works? This is the most radical option, and it's still debated because it makes testable predictions. Emergent gravity, developed by Eric Verlinde, proposes gravity arises from quantum systems maximizing entropy. Matter creates entanglement between spacetime's quantum degrees of freedom, producing an emergent force we perceive as gravity. In this framework, dark matter isn't stuff, but additional gravitational effect from vacuum energy displacement due to normal matter in a universe with positive cosmological constant. The math predicts galaxies should exhibit extra pull beyond visible matter, depending on cosmological constant, mass, and size. Verlinde's equations reproduce Mond-like behavior without dark matter particles and match cosmological observations Mond struggles with. The entanglement would link quantum states across cosmological distances. Every particle in a galaxy quantum mechanically connects to the cosmic horizon, and strain on that network from clumping matter generates the dark matter effect. It explains the Tully-Fisher relation, linking rotation speeds to visible mass, predicts right lensing amounts in clusters, accounts for cosmic microwave background features without dark matter. The problem is it's still developing. Some predictions match, others don't yet, and the framework needs work integrating with general relativity and quantum field theory. Critics argue it requires cosmological constant, fine-tuning, and unproven entropy assumptions. Supporters argue it's the only approach deriving dark matter effects from first principles, rather than adding particles. We spent a century looking for particles when we might have been looking at gravity wrong. And if true, the invisible majority doesn't exist. It never did. If this sparked your curiosity about what's out there, consider subscribing so you don't miss future space content. Thanks for watching.